My name is James McFarlane, and I am here to explain one of the most interesting demonstrations of the intermediate axis theorem in classical mechanics. Back in 2009, YouTuber Plasma Ben posted a video entitled Dancing T-Handle in Zero Gravity, which will be shown here. Now this free-floating rotation is undoubtedly an interesting one, as it demonstrates somewhat of a pseudo-bistable state in which the T-handle pauses at either states before oscillating to the other. In order to explain what is occurring, I need to mention some of the basics of the intermediate axis theorem. This theorem applies to rigid bodies with distinct shapes. A box, for example, as shown on the left, has a clear x, y, and z axes, as does the T-handle with axes x, y, and z as shown here on the right. The intermediate axis theorem states that rotation around the axes with the smallest and largest moments of inertia are stable, while the axis with the intermediate moment of inertia is unstable, and any disturbances while rotating about that axis will lead to a major disturbance from that orientation. Upon viewing the video, we can see that the axis that lies along the smaller part of the handle must be the intermediate axis. We can calculate the moment of inertia of the T-handle by treating the handle as two cylinders and summing the axial components of each cylinder. Before doing this, however, we will need to calculate the center of mass position. A center of mass calculation can be done by finding a mathematical relationship between the center of masses of the larger cylinder and the smaller cylinder. Here we find the position of our center of mass to be negative L over 5 plus 2R over 5. This corresponds to the assigned radii, masses, and lengths of the cylinders. Now that we have our center of mass position, we can use the moment of inertia equations I rotational parallel, 1/2 mr squared, and I rotational perpendicular, 1/4 mr squared plus 1/12 ml squared, as well as the parallel axis theorem, which allows us to apply these equations at a position other than the center of mass of the rotating body. In doing so, we will reach the calculations for the x, y, and z moments of inertia as shown below. It is these moment of inertia values that will be essential in forming our Python simulation. In order to mathematically explain the nature of the intermediate axis theorem, we need to take into account Euler's equations. Here we see that angular momentum and moment of inertia are related, and they're related to torque. However, in our system, a T-bar in zero gravity, we have a system with zero torque, as the only torque on the system would be gravity, however it is no longer present. As this is the case, we are able to rearrange our equation and have the equations shown here. It is important to note that the torque term is measured in the lab frame, while the angular velocity terms are measured in the body frame. The moment of inertia difference times the product of the omegas is actually an indication of the omega cross L term, which is because we are viewing L in two frames, the lab frame and the body frame. Say we have a theoretical system and an object is rotating about E3. In this system, omega 1 and omega 2 are very small, as omega 3 is the primary motion. As such, omega 3 can be taken as constant. As a result, we receive two first-order differential equations, as shown below. These equations can be rearranged through differentiation and substitution to yield one large second-order differential equation. What we can see here is that I3 can be either the smallest, intermediate, or largest solution, and if it's the smallest or largest, the solution will be a sine or a cosine. If the solution is sine or cosine, the system is stable, as it will simply oscillate back and forth. However, if I3 is intermediate, the solution will be an exponential, and it will be unstable as it drastically and quickly leaves from zero. This second possibility, where I3 is the intermediate, is what we are visualizing in the YouTube video of the dancing T-bar. There's another, more visual way of demonstrating this relationship. Poinsot's trick is a geometric representation formed by plotting rotational kinetic energy and the angular momenta squared on phase space. This will yield an ellipsoid which has two stable axes, omega 1 and omega 3 in this image. However, omega 2, which forms the third perpendicular axis, is unstable and, as shown earlier, will be the intermediate axis, which will result in an unstable rotation. Now that we have a sense as to the equations that will be used and the geometric representation for what rotations we will expect, we can investigate the rotation further in Python. Okay, so here is my Python program to model the T-bar's rotation. And I was able to adapt a program made last year by one of my fellow classmates, Luke Burnett. And I'll add a link to his video below because he's got a great video on some of the more kind of general aspects of the intermediate axis theorem. But essentially what we've got going on here is I have a compound object created from these two cylinders here, and using the moments of inertia as calculated earlier in the video, we plug in those moments into Euler's equations for a rigid body with zero torque in the lab frame. So with these equations, we're able to calculate individual omega x, omega y, and omega z. So angular momentum components in the x, y, and z directions. And from those, we're able to plug it into the rotation of the object and animate it. There's a lot of other code in here. A lot of it corresponds to some of the kind of nuances of the program. So we've got some arrows that explain some of the magnitudes of the individual components, as well as the total momentum, and then the graphical components too, which I'll show you. But let's animate it. So what we see here is obviously rotation very similar to what we would expect from that video. And what's very interesting is looking at the arrows on the object, RGB corresponds to XYZ. So we see that rotation along the Z-axis is clearly unstable. But what's interesting is that we can watch the individual X, Y, and Z components as they change, and the total angular momentum stays constant. Along with that, we have a constant total energy, and what's possibly most interesting is this periodic nature. So even though the rotation itself is unstable about the axis, it still kind of follows its own path and is periodic in nature. Now we can also show what the rotation would be like along the two stable axes, which I'll show next. Okay, so now that we've seen rotation around the intermediate axis, we can go back at our code and modify the initial angular velocity and view how the program responds to a different initial value. So say we do give it a value of 3 units in the y-axis, and we should see rotation that's stable around that axis rather than the flipping that we saw previously. And that is what we expect. So as we can see, the total angular momentum is still conserved, as is energy, and the 0.1 components in the x and z directions simply oscillate back and forth, but there is not an unstable axis, so the object doesn't flip as we see previously. Alright, so now we can return back one more time to our code and see what the rotation is like around the x-axis, which is our other stable axis in this object with this sort of symmetry. So we'll run the program, and rotating along the x-axis, we see another stable interaction. So although there is some sort of wobble that comes from the initial small angular momentum components in the y and z axis, we don't see any sort of flipping that we would see along the intermediate axis, which is consistent with the theorem. Okay, so I figured we'd take one last look back at the rotation on the intermediate axis. So I raised the rate to 1500 this time, which is 50% faster. And so we'll be able to look at it side by side with the video released by the International Space Station. And so what's so interesting about this rotation is that with the T-bar being the way it is, it looks so odd when it rotates and when it tumbles like that. But in reality, this rotation really isn't all that different than if you were to try and flip your phone or flip a book along its medium-sized axis as well. Well, thank you for watching my video on the Intermediate Axis Theorem. I hope you were able to learn something about the dancing T-handle and zero gravity. Thanks for watching.